Today's video is on one of the most important of the core practicals, and that is essentially capacitor discharge. And it's quite a complex core practical, this, because there are quite a few requirements that they want you to do. I will go through setting up the circuit, I will go through oscilloscope use, and whether you should or shouldn't when you're doing this experiment, and then changing out the resistors, changing out the capacitors, what effects that has, and being able to recognize what the graphs should look like. I'm going to show you the setup for the circuit, but the first thing that you should do is, in the picture here, when you choose your resistance, and the notes that come with this say you should use a 470 kilo ohm resistor. However, even though your resistor might say 470 kilo ohms, if you want to be accurate with your results, it is a good idea to actually measure the resistance of the resistor. And to do that, you simply set up a multimeter, make sure that you're in the correct range. So if you look up here at the ohms, you can see you get a range of possibilities for the resistance that you're measuring. Because you know that it's going to be around 470 ohms, then you choose a range that is going to work. Obviously, 200,000, between 0 and 200,000 here, that's not going to work because you know it's over 200,000. So we choose the 2 mega ohm range, and that's why we're getting a reading of 0.484. So that's telling us that it is 484 kilo ohms for our resistor. And this is the circuit that you're setting up. At the moment, you can see here, I have got it set up so that there's a voltmeter measuring the voltage across the capacitor. So if we zoom in on this picture again, this is our 6-volt power supply. This is our 100 microfarad capacitor. Here is our two-way switch, and I will talk you through the use of that in a moment. And the voltmeter, as you can see, is set on a range of 0 to 20 volts, and it is connected around the capacitor. Edexcel, in their method, suggest that instead of a voltmeter here, you connect an oscilloscope. And you can do this, though it does make the practical very tricky to do. This is their recommendation because they want you to learn about oscilloscopes. The data that I'm going to show today is taken using an actual voltmeter, but you can just as easily plug in an oscilloscope exactly the same way as you plug in the voltmeter. You take the 2 plugs that are put into the voltmeter and you put them into one of the channels on your oscilloscope and set your voltage range. Otherwise, the circuit is exactly the same. And if we look a bit more carefully at it, in our upper circuit here, you can see we have our power supply, we have running through the capacitor to this two-way switch and back to the power supply. So if you look at the two-way switch the way it is connected right now, you can see that it is connected to the upper circuit. That means that it is currently charging the capacitor, which is why we see a value of 5.95 volts on our voltmeter. To begin the experiment, you simply move this two-way switch here down so that it connects into this bottom circuit. And this bottom circuit is the capacitor, which is connected to the switch, down through the resistor at the bottom, and back up to the capacitor. And so essentially your capacitor acts like your power supply for the lower circuit. And what will happen is, as the energy runs through the lower circuit, the capacitor will lose its charge and you will see the voltage begin to drop. And this is the whole purpose of the experiment. So if we examine the circuit diagram, you can see this is your upper circuit for charging the capacitor. So there is your charging circuit, bringing the capacitor up to the same voltage as the EMF of the supply. And then you move the switch across. The capacitor is no longer being charged, so it begins to discharge through the resistor. And this resistor will determine how fast the current is able to flow from the capacitor, and therefore how fast your capacitor discharges. So remembering that we have 484 kilo ohms here for our resistor, and we have a 100 microfarad capacitor. Edexcel suggests that if you're using an oscilloscope, that you measure the times that it takes the capacitor to fall to specific voltages. So if you're starting with 6 volts, you might see how long it takes to 5.5, then 5, then 4.5, and 4, etc., etc., etc. So the voltage becomes your independent variable and the time you're dependent. If you're using a voltmeter, you're likely to look at the voltages every 30 seconds. Either way, you must make sure that you have plenty of readings. Because this is going to end up being a curve, we want to have lots of readings so we can see the nature of the curve. These results were taken using a voltmeter. You can see that the student has noted the EMF of the supply. They have written down the resistance of the discharging resistor, and they've also noted the capacitance of the capacitor. And just for themselves, they've written down the value of E over here. But if we look at the actual data, you can see that this person took the data every 10 seconds. And so they tracked the voltage every 10 seconds, and they did that 3 times and found a mean voltage, all the way down to 0.1 volts. What you should remember with a capacitor is that it always has what's called a tolerance. And the tolerance gives you how much the capacitance of the capacitor might deviate from the stated value. So the stated value in our capacitor is 100 microfarads. This particular capacitor had a tolerance of 5%, which is pretty good for a capacitor. They can be up to 20%. Now remember, if you're using an oscilloscope to do this, you will have voltage instead of time in this column, and then time instead of voltage or potential difference, and you will have repeats of the time it took to fall to particular voltage values. Either way, this is the graph that we plot at first. So you've got your PD across your capacitor on the y-axis and the time on the x-axis, and you see you get this curve. What we're interested in finding here is what's called the time constant for the capacitor. That's usually given the Greek symbol tau. You will see it as a small t as well. Or you sometimes see it written as RC, because for any resistor-capacitor combination, the time constant will be equal to the product of the resistance times the capacitance. So small t, tau, or RC, they all mean the same thing, and that is the time that it takes the voltage, in this case, to fall to 1 over E of its initial value. If you're not familiar with this concept of E, this is Euler's number. It's a constant number, a bit like pi. It is used for exponential graphs, which is what this is, and so it's just a value, and 1 over E becomes a value. And 1 over E is 0.368. Sometimes you see that rounded to 37%. So the time it takes a capacitor to fall to 37% of its initial value. Our initial value was 5.95 volts, so we're going to multiply that by 0.368, and we end up with a value of 2.1896. What we do then, very like radioactive decay, is we find this value of 2.1896 on our y-axis. If you're plotting this by hand, it's going to be much easier for you to find exactly where the 2.1896 is, even if you don't get to that many significant figures. You then go across and go down and find out what the time here is, which I have measured to be 48 seconds. So that is telling us that the time constant for this capacitor-resistor combination should be 48 seconds. The time that it takes to fall to 1 over E of its initial value of voltage should be 48 seconds. We know that that time constant is equal to R times C. And since we went ahead and measured R at the very beginning, we can then calculate a value for the capacitance from this, because 48 seconds divided by 484,000 gives you a capacitance value of 99.2. Remember, the nominal value of our capacitor was 100 microfarads. We do have a 5% tolerance. We get a value of 99.2 microfarads here. And we'll come back to this later to look at our uncertainties and whether our uncertainties work within the tolerance for the capacitor. Meantime, there is a second graph that you can plot. Before we do that, I should mention that if you are asked in any exam situation to find the time constant of a capacitor from a graph like this, do not just do 1 over E once. So find the first value of 1 over E, that is 37 or 36.8% of your initial value, and then do that again for 2.1896. So find 36.8% of that, go down and across again. So find your RC a second time and a third time and find an average. Our second method involves using the natural log. This is the equation that determines the rate at which the capacitor voltage will drop. And so as we can see, it's an exponential equation. We can log, or take the natural logs of both sides of this equation, giving us ln V is equal to ln V0 minus T over RC. And I'm going to rearrange this a little. The reason I did that rearrangement is because that then gives you y is equal to mx plus c. So we know, based upon this rearrangement, that if we plot ln V on our y-axis and t on our x-axis, we should get a straight line with a positive intercept, that's what the c is, and a negative gradient. And then we can use the value of that gradient to determine our RC, which remember is our time constant. So this is a second method for finding RC. The fact that we have a straight line means that if you're doing this by hand, you're likely to be able to draw a better line of best fit, and so this is likely to give you a more accurate value. This is why we have this table here of time against the natural log of V. Now please note, anytime you write at the top of a table or on the axes of your graph, you are writing the log of a value, it must be in this format. ln, open bracket, you can write volts or potential difference or voltage with a slash and the unit with the closed bracket. This is the way that Edexcel are insisting you write any log like this. When we plot this graph, then we do indeed get a straight line with a negative gradient. The beauty about doing it with Excel is that you can get Excel to show you the equation. Otherwise, you are finding the gradient of this manually if you've done it by hand, which is absolutely fine. We can see here that our gradient is minus 0.203. And remember, that gradient is equal to minus 1 over RC. So we can use this gradient value to find a value for our time constant. When we do that, we end up with a time constant of 49.26 seconds. And we're going to do the same as we did with the first graph, is use that time constant, remembering that T is equal to RC. So this value of 49.26 is equal to R times C. So if we divide 49.26 by our known resistance value, we get a value of 101.2 microfarads. So now we've got two values for our capacitance based upon the two different graphs that we've drawn. What we'd like to know is what our percentage uncertainty is. And so to do this, we use half the range of our repeats. If, again, you've done this with an oscilloscope, you'll be doing half the range of the time repeats. Here with this data, you pick a median value, and you get half the range of your voltage repeats. And so half our range is 0.01 volts. When you put 0.01 over 0.76 and multiply by 100, you get a percentage uncertainty of 1.32%. Okay, now what are we going to do with this? Well, our capacitance from graph 1 was 99.2 microfarads. If we then add our uncertainty from our values onto that, that gives us an uncertainty in our capacitance of 1.31 microfarads. And so our range of possibilities based upon our uncertainty is 97.9 to 100.5. And if we do the same process for graph 2, adding on the 1.32% of 101.2, we end up with a range of this. Now we know that the capacitance of our capacitor was 100 microfarads, and it has a tolerance of 5%. Remembering the tolerance meaning the deviation from that stated value. So we can see for both our graphs, we are getting, even with our uncertainty, we are getting values within the 5% tolerance of our capacitor. There is a second way you could do it. You could find the actual RC value based upon the numbers, including the tolerance of the capacitor. So if we have 484,000 as our R, and the highest possible value of the capacitance, which is 105 microfarads, that gives us a time constant of 50.82 seconds. And we do the same with the lowest possible value of our capacitance, giving us 45.98 seconds. And so our time constants that we got should lie between these two. And considering the two time constants we got were 48 seconds and 49.26 seconds, it does lie within the tolerance of the capacitor. It is the second part of this practical where the real fun starts, and what I think they truly want you to use the oscilloscope for, because they want you to be able to understand oscilloscope traces. So what they suggest you do is you set up a power supply unit, and this supply unit is one that can supply a square wave AC waveform. And they suggest that you set that square wave to be produced at 50 Hertz. A square wave is essentially an AC wave. We know that an AC waveform usually looks like that. And what the square wave one is, the same idea, except it gives you a fixed voltage in the positive and then flips to a fixed voltage in the negative, and so on. They then suggest that you put a 4.7 microfarad non-electrolytic capacitor in series with a resistor in this circuit. Non-electrolytic means that it is non-polarized. So normally when we connect in capacitors, they have a positive and a negative end, and you have to make sure that you connect them in correctly. With non-electrolytic ones, it doesn't matter which way you connect them in. And this is, of course, useful for an AC waveform like this, because the capacitor will charge whether the voltage is in the positive or whether the voltage is in the negative. You are then to put the oscilloscope around the resistor and measure the voltages across this resistance. So let's think for a moment what it is that is going to happen here. They suggest that you set your power supply unit, your square wave generator, to 3 volts and 50 Hertz. 50 Hertz means, of course, that you're going to get one complete cycle in 1/50 seconds. The 3 volts, now remember that 3 volts, because these two components are in series, that 3 volts is going to be shared between those components at all times. When you first turn the circuit on, the capacitor will have 0 voltage across it, which means that your resistor will have all 3 volts. But as the capacitor charges up, its voltage is going to increase, meaning that the 3 volts across the resistor is going to decrease. And this is what we're tracking over time. And then Edexcel suggests you change out the resistance here and see what happens with the oscilloscope trace that you get. And these are the really interesting oscilloscope traces. This is what a square wave pattern actually looks like. You can see in this particular one, it is 1.5 volts. So you have positive 1.5 volts for the first half of the cycle, and then negative 1.5 volts for the second half of the cycle, and so on. So we start with a resistance of 1000 ohms and our 4.7 microfarad capacitor. This is the trace that you get. So remember, we are tracking the voltage across the resistor. We can see, let's start at this point here. And this is where the direction of the voltage changes. So as soon as the supply changes direction, the resistor is at maximum voltage. And then as the capacitor charges up, that voltage starts to share between the capacitor and the resistor. The voltage across the resistor decreases like this. And it will decrease according to the rate at which the capacitor charges. So what we're really seeing here is the capacitor charging and how quickly the capacitor will charge. And you'll see when we look at some other resistors that there are distinct differences between them. Now what Edexcel suggests you do is that you estimate the RC of the capacitor charging based upon this. And of course, we do RC in exactly the same way as we did before. RC is the time it takes to fall to 1 over E, or 36.8% of the maximum value. And although we're measuring the voltage of the resistor here, it will fall to 36.8% of its voltage value in the same time as the capacitor rises to 36.8% of its voltage value. The first thing that we need is the maximum voltage. And so if you look, I've drawn in the lines previously. If you look up here, you can see the initial voltage is 8.4%. So our 8.4 volts. 8.4 volts. Then if you multiply that by 0.368, that's 36.8%, you get 3.09 volts. So then you go across, you'd find 3.09, which just so happens to be where the dark blue line starts here. More or less anyway, it's an estimation. Go across and go down, and so you're finding the time it took to go from that 8.4 to this 3.09. And if you look carefully at the scale there, you can see that looks like 4.5 milliseconds. We can see how close we were by doing an actual calculation of the RC. We know that it is 1000 ohms and 4.7 microfarads, and if we multiply those two together, we see we get 4.7 milliseconds. It's pretty close. The next value suggested by Edexcel is to change out that resistor and put in a 470 ohm resistor. Now, we should realize, of course, that when we have lower resistance in our circuit, our capacitor is going to charge more quickly, which means that the voltage across the resistor is going to decrease more quickly. And this is indeed what these lines are showing us. You can see we're getting a much steeper fall here than we did before. And so the capacitor is charging up to its maximum voltage, which will be the same as the supply. And as it does that, the resistor's value drops. And of course, remember, because this is a non-electrolytic capacitor, the exact same thing happens in the opposite direction. So when the supply direction changes and it goes negative, the value of the voltage for the resistor is just simply a negative, and it decreases, as in decreasing in magnitude, in exactly the same way. And so again, we can look at the RC for this. If we look at our maximum voltage, that's 9.2 volts. So our VO is 9.2 volts. Multiply that by our 36.8% again, and we get a value of 3.39 volts. So we go along to our y-axis, find 3.39, go across and go down, and we want the time it took to go from that maximum to that value of 1 over E. And you can see it's a much shorter time here. This time our RC is 2.3 milliseconds. And again, if we do the calculation of R multiplied by C, our actual RC, which is 470 ohms times 4.7 microfarads, is 2.21 milliseconds. So far, we've started with 1000 ohms. We decreased to 470 ohms and we noticed a much steeper fall. This time we are increasing to 2200 ohms, and we should expect that we're going to get much less of a fall because the capacitor is going to charge much more slowly, because this resistor is going to slow down the current which is charging the capacitor in the circuit. And that is exactly what we see. Remember, we're getting exactly the same in positive or negative. That is, as the supply switches, we start the cycle again. So our resistor goes to maximum voltage, and then the magnitude of that decreases and it heads down towards zero. But of course, it's doing it much more slowly here because the capacitor is charging more slowly. Again, let's look at our RC values. So our VO this time was 7 volts. Multiply that by our 0.368, and we get a value of 2.58 volts. And if we find 2.58, go across and go down, it actually just reaches 1 over E by the time the power supply switches the direction of the current. And we see that we get an RC here of 9 milliseconds. The actual RC that goes with this, multiplying them out again, is actually 10.3 milliseconds. So a little less accurate with this one, possibly because of the nature of the trace and exactly where we drew our lines. What do you take away from this? You should be able to look at these curves and be able to explain what is happening when the power supply is in the positive up here and what is happening when it is in the negative. Why are you getting these curves that look the same but in opposite directions? You should be able to explain the idea of a non-electrolytic capacitor, and you should be able to use these graphs to find a value for RC. So this idea of 36.8% is very, very important. You also need to understand the nature of the fact that they're in series. We are measuring, remember, the voltage across the resistor, which is in series with the capacitor. When you first turn on the circuit, the voltage across the resistor is going to be at a maximum, and the voltage across the capacitor, because it is not charged up, is going to be at 0. And that changes as the capacitor charges. And so what we're seeing here, although we're measuring the voltage across the resistor, is the equivalent to the capacitor's voltage charging up.